Hello everyone, thanks for logging into today's webinar. We appreciate you taking the time out of your day to attend. My name is Justin Nickel and I joined EXAIR in 2014 as an application engineer. My previous background includes over 15 years of industrial fluid handling experience involving industrial pumps, mechanical seals, valves, and automation. For over 34 years, EXAIR has been manufacturing intelligent compressed air products for the industrial marketplace. We are located in Cincinnati, Ohio, and we provide both domestic and international sales. Our products are commonly used in cooling, cleaning, static elimination, and conveying processes. In fact, you may be familiar with some of our products like our super air nozzles, vortex tubes, cabinet coolers, or industrial vacuums, to name a few. We also offer the largest selection of end-use intelligent products in the market today. Much of our focus here at EXAIR is to improve the overall efficiency of industrial compressed air operating processes and point-of-use compressed air operated products. Over the course of the next 30 to 45 minutes, we want to provide a better understanding of the cost of compressed air and how tracking and monitoring your current system can help identify areas where operational improvements could be made. In many cases, improving your compressed air system can seem a huge undertaking with air audits, system controls, or new compressors. We want to focus on the simple steps you can take to reduce your air consumption while still maintaining your system's effectiveness. Finally, we will demonstrate how utilizing an engineered solution can help optimize your current compressed air system, in many cases reducing energy costs related to compressed air waste, leading to a more economical operation. This information should be helpful to energy auditors, managers, engineers, operators, or anyone involved with maintaining or using compressed air. From pneumatic hand tools like impact wrenches or nail guns to larger scale industrial applications like stamping presses, the use of compressed air can be found in almost any industry. It is often referred to as a fourth utility next to water, gas, and electric, and in many cases is the largest energy user in an industrial plant. The generation of compressed air accounts for approximately 1/3 of all energy costs in an industrial facility, and up to 30% of that compressed air is wasted through inefficient operation and leaks. In addition to simply wasting money, compressed air leaks can also contribute to a variety of other operating losses. A leak can cause a drop in system pressure, reducing the performance of end-use devices, which can have an adverse effect on production. A small leak may not be that noticeable, but several small leaks can lead to significant energy costs. With an average cost of 25 cents per 1,000 standard cubic feet, compressed air can be expensive to produce, so it is very important to use this utility as efficiently as possible. Let's look at the cost of compressed air. Many plants know their energy cost, but if not, an industry average is 25 cents for every 1,000 standard cubic feet used. To get a better understanding of what this means, let's look at the following example. The cost will vary greatly across the country as utility rates change. If you know that your electricity rate is significantly higher than 8 cents per kilowatt hour, you should follow along with the slides and do your own calculation. We start with a 20 horsepower compressor, which requires 15 kilowatts. At 8 cents per kilowatt hour, the 20 horsepower compressor costs $1.20 per hour to operate. If you have trouble calculating your usage, contact me or EXAIR after the webinar and we can run through the calculation. A 20 horsepower compressor running at maximum output will produce 80 standard cubic feet per minute or 4,800 standard cubic feet per hour. 4 SCFM per horsepower is a conservative rule of thumb. Some air compressors can make 5 or more SCFM per horsepower, but individual compressors and delivery rates may vary. To produce 1,000 SCF will take 0.2083 hours or 12.5 minutes. Taking the cost of $1.20 per hour to run a 20 horsepower compressor times 0.2083 hours, the time it takes to produce 1,000 SCF, equals 25 cents for every 1,000 SCF generated. You will see this figure in most reference material as it's a very reasonable number in the Midwest, but is conservative in Europe and other parts of the country. Let's talk about artificial demand. So what is it? According to the Compressed Air Challenge, the amount of excess air volume that is created by supplying higher than necessary line pressure for point-of-use compressed air applications. With fluctuating supply pressures, the artificial demand on the system varies, raising and lowering the amount of energy being lost to waste. A more simple explanation would be that plant personnel or operators increase the supply pressure in an effort to improve the end-use device's performance. But when the pressure is maxed out and they can't increase the pressure any higher, the line pressure will actually begin to drop, indicating potential leaks in the system. As a result, performance begins to deteriorate in certain areas. This not only puts stress on the existing compressor, now that it's having to operate longer, but it also leads to the false idea that a larger or secondary compressor is needed. Here's an example of how operating pressure can directly affect operating costs. We are showing our model 1100 Super Air Nozzle, which at 80 psig uses 14 standard cubic feet per minute. Based on the average operating cost of 25 cents per 1,000 SCF used, it would cost 21 cents per hour or $1.68 to operate this nozzle for an 8-hour shift. If we were to use the same model 1100 Super Air Nozzle, but now drop the operating pressure to 40 psig, the air demand would decrease to only 8.1 SCFM, reducing the hourly cost to 12 cents or an 8-hour operating cost of 96 cents, a 72-cent reduction. This could lead to over $750 in savings annually. Leaks in a compressed air system can waste thousands of dollars of electricity per year. In fact, in many plants, the leakage can account for up to 30% of the total operational cost of the compressor. Some of the most common areas where you might find a leak would be at connection joints like valves, unions, couplings, fittings, etc. This not only wastes energy, but it can also cause the compressed air system to lose pressure, which reduces the end-use product's performance, like an air-operated actuator being unable to close a valve, for instance. In this table, you will see that a certain amount of air volume is lost through an orifice or opening. Referencing back to the 20 horsepower compressor we discussed earlier and how it produces 80 standard cubic feet per minute, as you can see, if you have several leaks throughout your facility, it isn't going to take long for the waste and high operating costs to quickly add up, as well as potential increases in repair or maintenance costs for the existing compressor. One way to estimate how much leakage a system has is by using a downstream pressure gauge from a receiver tank. You would need to know the total volume in the system at this point, though, to accurately estimate the leakage. As the compressor starts to cycle on, you want to allow the system to reach the nominal operating pressure for the process and record the length of time it takes for the pressure to drop to a lower level. The 1.25 multiplier corrects leakage to normal system pressure, allowing for reduced leakage with fallen system pressure. The industry average shows that with any leakage more than 10%, there are areas where improvements could be made in the system. If you don't know the volume of air that your compressor produces, another method to estimate how much leakage a system has is to turn off all of the point-of-use devices or pneumatic tools, then start the compressor to bring the system to normal operating conditions. Record the average time it takes for the compressor to cycle on and off as the pressure drops due to the lost air through the leaks. The total percentage of leakage can be calculated by taking the operating time divided by the total time and multiplying times 100. Again, any leakage more than 10% shows that improvements could be made in the system. Many times, plants will think just to add another compressor online to provide the additional capacity to maintain a constant workflow. While this may seem like a good idea at the time, you aren't addressing the real problem, such as leaks in wasteful end-use devices like open pipe. Not to mention that an industrial-sized air compressor is going to be a large capital investment with high installation and maintenance costs. Let's take a look at the following example. In this case study, a customer was looking to reduce their air usage so they didn't have to purchase an additional compressor. They were using 86 open copper tubes for general blow-off applications throughout their facility, with flows as high as 475 standard cubic feet a minute during peak operation and an average demand close to 190 SCFM. Their existing 50 horsepower compressor didn't produce enough volume to keep up with the full demand, which caused the system to lose pressure. The company decided to have an air auditor evaluate the existing system, and after completing their inspection, instead of purchasing a new compressor, the consultant recommended installing an engineered solution to replace the wasteful open tube blow-offs. By switching to an engineered solution, not only were they reducing their air usage, but they were able to operate at a lower pressure as well. By retrofitting an energy-efficient solution to each tube, they were able to reduce their air usage by 43%, using 275 standard cubic feet per minute during peak operation and only 70 SCFM for average use. Not only did this save the company over $9,000 in operating costs, but by making the existing compressor operate more efficient, it eliminated the need for the additional 50 horsepower compressor, saving them an additional $24,000. Understanding your demand side will help figure out how much compressed air is currently asked for and why are you asking the supply side for that air. This will allow you to gather information on where the savings are possible in order to make educated adjustments within your compressed air system. You want to start documenting your demands, showing each point of compressed air use. Start at your compressor and follow the compressed air lines to each drop that has a point of use, like an air gun or blow-off nozzle. Record the volume of air that each device is using at a given pressure and the length of time that it's being used, as well as the length of time that it's off. Once you have all of the point of use devices recorded, you can then begin to look at the areas you have for improvement. For example, if you have several duplicate processes but only one location needs a higher operating pressure than others, that would be an ideal location to look at why you need the higher pressure. Okay, that was a lot of information, so let's do a quick recap. We discussed how to calculate the cost of compressed air and explained how creating artificial demand can lead to expensive waste. We showed how monitoring the current system can help you identify improvement areas to reduce waste, leading to operational cost reduction and unnecessary capital expense. Now let's take a look at how following just a few simple steps can help optimize the current system and reduce your compressed air usage. As we mentioned earlier, the first step you want to consider is measuring the air usage in the system. If the demand exceeds the supply, there is potential for problems to arise, such as lowered pressure and force from compressed air operated devices leading to irregular performance. To relate this to everyday situations, think of banking. Most people or businesses have systems in place to monitor their accounts, ensuring that there is always enough of a balance in their account to cover their expenses. The same principle would apply here. By measuring your compressed air usage, you can locate the source of high usage areas. Monitor the usage on each leg of the system. Again, to do this, you want to start at the compressor and check individual leads to each drop point to a blow-off device. Record your findings to track the demand. EXAIR's digital flow meters are designed to measure flow continuously and accurately to give you real-time flow measurements of your compressed air system to help identify problems. You don't need to weld, cut, or disassemble pipelines to install. With a drill guide, the digital flow meter can be easily mounted onto the pipe. The digital flow meter measures flow by comparative analysis with thermal dispersion, so the accuracy is very high and recalibration is not required. Step 2 is to locate the source of waste. As we discussed earlier, compressed air leaks can result in a waste of up to 30% of a facility's compressor output. A compressed air leak detection and repair program can save a facility this wasted air. Implementing such a program can be used as a way for a facility to find additional air compressor capacity for new projects instead of having to purchase additional compressors to make up for the leakage. Whenever a leak occurs, it will generate an ultrasonic noise. Ultrasonic sound is a range of sound that is above the human hearing capacity. Typically, humans can hear frequencies from 20 Hz to 20 kHz, with sound from 20 kHz to 100 kHz being termed ultrasonic. Turbulence created by air or a gas forced through a small orifice generates ultrasonic sound. Ultrasonic sound is very directional in nature. This directionality is used to pinpoint the exact origin of the sound source, the leak point. The greater the pressure difference across an opening, the greater the velocity. As the velocity increases, the frequency of the emitted ultrasonic sound will become higher, producing white noise or the broadband emission of sound. Our ultrasonic leak detector is designed to locate the source of ultrasonic sound emissions up to 20 feet away. These ultrasonic sound emissions are converted to a range that can be heard by humans. The sound is 32 times lower in frequency than the sound being received, making the inaudible leaks audible through the included headphones, and the LED display gives a visual representation of the leak. Many open pipes or homemade blow-offs not only waste compressed air, but can also be dangerous to operate as they typically violate OSHA safety standards by generating loud noise. The third step involves finding the source of these noisy and wasteful blow-offs and replacing them with an energy-efficient engineered solution. By replacing these devices, you are not only reducing the amount of waste, but also improving operator safety by complying with OSHA safety requirements, avoiding potential costly fines. For comparison, let's look at a 1/4-inch open copper tube. 1/4-inch open copper tube, when operated at 80 psig, will consume 33 standard cubic feet per minute. This adds up to roughly $3.96 per 8-hour shift. Intelligent compressed air products like EXAIR Super Air Nozzle provide an engineered solution that can reduce air consumption and noise. By replacing the 1/4-inch open copper tube with an engineered solution, like our 1/4-inch MPT Model 1100 Super Air Nozzle, and keeping the operating pressure the same at 80 psig, you will reduce the air demand to 14 standard cubic feet per minute. Now the operating cost has been reduced from $3.96 to only $1.68 per 8-hour shift, or an annual savings over $2,400. Taking an even closer look at the 1/4-inch open copper tube versus our 1/4-inch Model 1100 Super Air Nozzle, you can see the dangerous sound level of 102 decibel produced by the open tube. Per OSHA standard CFR 1910.95A, this would limit the exposure time to less than 2 hours total per day. In addition, the open copper tube provides no relief or control to reduce the outlet pressure below 30 psi if the device were to be blocked by the skin, therefore not meeting OSHA standard 29 CFR 1910.242B. With our Model 1100, the sound level is only 74 decibel, well within the OSHA standard. And the air is exhausted below an array of fins, so it is always able to vent freely, never getting above 30 psi if dead-ended. Here we show another case study we recently published. In this example, the customer was looking for a replacement blow-off device that would reduce air consumption and the noise level to meet OSHA standards. The company had 65 stamping presses, each fitted with 2 1/4-inch open pipes for part ejection. Each pipe consumed 23.2 standard cubic feet per minute, or a total air demand of 3,017 SCFM, using almost their entire compressed air output capacity. The existing blow-offs produce noise levels well above acceptable hearing levels per OSHA requirements, which required hearing protection for the operators. By installing our Model 1100 Super Air Nozzles on each existing noisy open pipe blow-off, the air consumption was reduced from 23.2 SCFM to only 14 SCFM for a 40% total reduction in air demand. This calculated out to an estimated $45,000 of energy savings per year. In addition, the sound levels were reduced to 74 dBA, meeting OSHA requirements and eliminating the need for additional hearing protection. Not to mention, they were able to identify other loud noise sources as well. EXAIR's digital sound level meter is an easy-to-use instrument that measures and monitors the sound level pressure in a wide variety of industrial environments. The source of loud noises can be quickly identified so that corrective measures can be taken to keep sound levels at or below OSHA maximum allowable exposure limits. The sound meter comes from the factory with NIST certification. The easiest way to reduce compressed air usage and save on operating expense is to turn off the compressed air to a device when it isn't needed, step 4 in the process. Not only will this save money, in many cases, it can also simplify a process for the operator. A simple manual ball valve and a responsible operator can provide savings at every opportunity to shut down the airflow. For automated solutions, a solenoid valve can be operated from a machine's control. For example, if the machine is off or a conveyor is stopped, close the solenoid valve and save the air. A foot pedal valve offers a hands-free solution to activate an air-operated device only when needed, such as being implemented in an operator's workstation. For even more control, you can use a device like our electronic flow control, or EFC. This helps minimize compressed air usage by incorporating a programmable timing-controlled photoelectric sensor to turn off the compressed air supply when there are no parts present. It is suited for NEMA 4 environments and can be easily wired for 100 to 240 VAC. Step 5. Intermediate storage. Some applications require an intermittent demand for a high volume of compressed air. This can cause fluctuations in pressure and volume throughout the system, starving certain areas of compressed air. A common mistake is to increase the pressure at the compressor. This doesn't solve the problem, it only masks it. In some cases, you are actually causing more waste. Remember artificial demand we talked about earlier? Increasing system pressure by 10 psi results in a 5% increase in energy cost on average. By installing a receiver tank near the point of high demand, there is an additional supply of compressed air available for a short duration. This will help eliminate fluctuations in pressure and volume. EXAIR offers a 60-gallon ASME-approved vertical steel tank with mounting feet for easy installation near high-demand processes. Step 6. Controlling operating pressure. Many pneumatic product manufacturers have a certain set of specifications regarding performance at stated input pressure. In many applications, or in the case of using a homemade blow-off device like open pipe, these wouldn't necessarily require the full rated performance of the device or full line pressure. Controlling the air pressure at the point of use device will help to minimize air consumption and waste. After all, the more pressure you put into an orifice, the greater the volume of air that will pass through it. By simply installing a pressure regulator on the supply side, you can start off at a low pressure setting and increase the pressure until the desired result is achieved. Not only will this help to conserve energy by only using the amount of air required for the application, it also allows you to fine-tune the performance of the point of use device to match the application requirements. We understand that not all companies or facilities have the resources available to perform the steps we discussed. EXAIR offers a free service where you can send us a sample of the product or products you use for your applications, and using our calibrated testing equipment, we can compare the performance of your existing product to an EXAIR engineered solution. During our testing, we can determine air consumption, noise level and force, and publish a comprehensive report, including a cost savings analysis. Here's an example of a recently published efficiency lab report. We will provide the objective of the test, the current application or process, and the procedure we follow to perform the testing. We will show the performance test results for the existing product compared to the performance specs of the recommended EXAIR engineered solution. In conclusion, we will provide a summary of our findings as well as a recommendation for optimizing the current process. This concludes our presentation, and at this time we'd like to answer any questions about the information covered here today. One of the first ones is, I am using an open copper tube. How would I adapt one of your nozzles? The easiest way would be to use a compression fitting to an MPT adapter. Next, how would a clogged filter affect performance? We recommend to check the pressure drop across filters once you see more than a 5 psi drop. That is when performance could be negatively affected. Next one here, how would I take advantage of your efficiency lab? You can contact an application engineer and we will make arrangements so you can send a sample of your product in for performance testing. Another one comes in, the impact is important. So I think what you're saying here is how the air contacts the part. Yes, distance, pressure, angle, all are going to come into play for effective blow off. That's something you're going to need to adjust to fit the application, but those are going to be important. Does the tool you show calculate the savings value of the leak? The ultrasonic leak detector has no storage. It's just going to indicate the approximate amplitude of an ultrasonic sound wave. Could you review the 2 OSHA regulations again, please? Sure. The first one is going to relate to sound. At 90 decibel, OSHA limits the exposure time to 8 hours per day. Around 104, 105 dBA, it's limited to about half an hour. So they don't really recommend a specific product. They just have 2 methods that you can go about gaining compliance. The first is going to be to use an engineered solution. The second is going to be reduce your operating pressure. That would fall into the second OSHA standard. The second one is related to 30 psi dead end pressure. So what that means is if you have an outlet pressure greater than 30 psi and you were to block that outlet of that nozzle or open pipe against the skin, you can actually introduce air into the bloodstream, which can be fatal, causes what they call an air embolism, cause stroke, death. So the way you would go about that would be to drop your operating pressure for your device less than 30 psi. Of course, that's going to limit the effectiveness of what you're trying to do to the application. You're going to reduce your flow, your force. The other method to go about is an engineered solution. That's going to reduce the air outlet pressure, which is what our devices do. So they create the restriction so your outlet pressure is never going to get above that 30 psi threshold. See here, got any more coming in? Another one, what's the difference between air pressure and a blower? Okay, so an air compressor is going to create high volume, or CFM, SCFM, at high pressure. A blower is going to build a lot of CFM, a lot of volume, but they're not necessarily going to build pressure. In addition, blower systems need a large footprint for installation. There's also a lot of operating and maintenance costs associated to them. Bearings, things like that need to be replaced. You don't have that with a compressed air system. See here. Another one coming in. For pneumatic equipment, do you have a pressure recommendation? It's really going to depend on the application. We always mention around 80 to 100 psi is a good place to start. A lot of our air nozzles and that performance specs are based on 80 psi. Again, using a regulator on your supply line and adjusting your pressure to fit the application is going to be key. But most blow-off applications, 80 is a good place to start, and then you can cycle from there. See, coming in here. Okay. A few seem to be, there'll be a recording or available, of the presentation? Yes. In the next few days, we hope to have a presentation on our website. You'll get an email link to register for that, and then you'll have access. So hopefully you'll have that done here in the next short bit. Anything else? Okay, well that looks like it's it. Again, I just want to thank everyone for participating in today's session. If we can help in any way, please feel free to contact me or another application engineer at 1-800-903-9247. I will be happy to help you. Hope everyone has a great day.